All right, guys, we're going to go ahead and work through the final exam practice. And so here we go. Pauses are needed, and good luck. Here we go. So this is going to be our final exam practice key. We've got the formula sheet here in case we need it, and beet juice for strength. So good to go. All right. So we're going to find the domain of this function. Okay, well, to find the domain, we just want to know which t values are possible. So this is, which t values are possible. And we see that there's a log, so we know that we can't take the ln of negative values, which means we're going to need to have the inside 2t cubed minus 12 to be greater than 0, right? Here we're actually going to need greater than. I'm not so concerned if it's greater than or equal to then. You can't really take a log of 0, but so we're going to want strictly greater than. So here 2t cubed, so we're going to have 2t cubed is greater than 12. So we're going to keep this inequality, right? We have t cubed is greater than 6, dividing by 2. And then we're going to have that t is greater than the cube root of 6. That's really it. We're done. So this the cube root of 6, of course, is going to have to be a positive number because, it's a third power, so negatives would stay negative. So it's going to be one number, right? It's not going to be a plus or minus. The cube root of 6 is a positive number. And so that's it. We're going to have t greater than 6. This is our any reasonable notation. Interval notation would be we're going to have t, in the interval from the cube root of 6 to infinity. Open and open. Right? Okay, great. That's number one. All right, we have two equations to solve here. So the trick with these, is figuring out, okay, we can get them in the same base, right? There's really two ways to go. So we can do the same base, right? We're going to have 16 x plus 7, and we notice that 256 is the same as 16 squared, right, raised to the 5x minus 2. Powers like this, we multiply, right? This is an important part. 16x plus 7 equals 16 to the 10x minus 4, right? And now, because these are the same base, these exponents must be the same. So x plus 7 equals 10x minus 4. And so we're going to have 9x, right? So if we move that over here, add that equals 11. So x equals 11 ninths, right? 9, right? 11. Okay, so we're good. And another way to do that, that's how I would recommend doing these. A second way to do this would be you can take the log of both sides. So we have ln of 16. Well, here, let's try this. You could do the ln. Let's do the ln. ln of 16 to the x plus 7 equals ln of 256 to the 5x minus 2, right? By the power of logs, we can drop this down. So we get x plus 7 times ln, x plus 7 times ln of 16 equals 5x minus 2 times the ln of 256, right? And so we're going to have, we can solve this, right? So we're going to want to solve for x. So here we have ln of 16, x ln of 16 plus 7 ln of 16 equals x times 5 ln 256 minus 2 ln 256. So we bring the x's together. We have x ln 16 minus x times 5 ln 256 equals minus 2 ln 256 plus 7 ln 16. Again, by the powers of logs, we can see that this is a minus 2. We could put this back as a power on the ln, but we don't need to. So we can factor out, right? We're going to have, in this case, x is minus 2 ln of 256 plus, again, we're going to have, we had to add this over, so minus 7 ln of 16, and then we divide by what we factored out here, which would be ln of 16 minus 5 ln of 256. Right? This is not 11 ninths. right? How could you do that? You could change base on all these. It would be a lot of work, but you could do it, right? Right, like you could write ln of 256 is ln of 16 squared, and then you could bring the 2's down, right? Right, would that work? Something like that, right? We can do it, right, if we keep going. So this is going to be minus 2 times ln of 16 squared minus 7 ln of 16 all over ln 16 minus 5 ln 16 squared. So it's going to be minus 4 ln 16 minus 7 ln 16 all over, what do we have, ln 16 minus, bring the 2 down, minus 10 ln 16. And so, of course, this is going to be minus 11 on the top, and this is going to be minus 9. So we pull out an ln 16. So it's ln 16 on the top, minus 4, minus 7. And then ln 16 on the bottom, pull out. We're going to have 1 minus 10. Right, ln 16's cancel, and this is minus 11 over minus 9, or 11 over 9. Phew, that was a lot of work. Another way we could go about doing it that would be easier than ln's, right, is we could take the log base 4 of both sides, so log base 4 of 16 to x plus 7, or we could take log base 16. Log base 4 would help too. Log base 16, right, equals log base 16 of 256, 5x minus 2. Similarly, we bring the powers down, so of x plus 7, right, times log base 16 of 16 equals 5x minus 2 times log base 16 of 256. Well, log base 16 of 16 is 1, and log base 16 of 256 is 2. So 1 through there and 2 through there, we end up at the same place we were here, right? So this ends up here, and you're going to get the same answer, right? Using the log base here, we simplified things, right? Okay, phew, that was a lot for that problem. Of course, it's a quick problem. So log base x of 243 equals minus 5. Of course, there's going to be a few ways to do this too. The most immediate way, and the way that I had envisioned you doing this problem, is by rewriting it. So log base x of 243 equals minus 5. So this means the exponent on x that gives you 243 is minus 5. So you can write this as x to the minus 5 equals 243. From here, right, you could do this a few different ways, right? You could take the log of both sides, you know, whatever you want to do, but that would bring the power down. One thing you could do is you could rewrite this. So this is 1 over x to the 5th equals 243 over 1, of course. And so if you cross multiply, right, you're going to have, that's what the negative power did. So you're going to have x to the 5th times 243 equals 1. X to the 5th equals 1 over 243. This is the same effect as if we took both to the minus 1 power. We inverted both sides here. That's what we did to get here. But we started by rewriting that and cross multiplying. Same effect. So here we can, for this one, now we can take the 5th root. So x is going to be the 5th root of 1 over 243, which is going to be 1 over the 5th root of 243, right, which is 1/3. Right, 3 cubed is 243, right? 3, 9, 27, 81, 243. Right, of course you guys know this. Right, another way, okay, so you rewrote it. How else would we do this? We would raise both sides, x to the minus 5. Raise both sides to the negative 1/5, right? Because that's what's going to cancel that. It's going to be 243 to the negative 1/5, right? And so, of course, this cancels, so we have x, and we do the negatives. So this is 1 over 243 to the 1/5, right? And, of course, we know that this is 1/3, right? We're good. This is the 5th root of 243, right, which we can write as the 5th root. Phew, how else could you do it? Well, another way to do it would be to raise, you're going to end up with this equation. Another way, you could raise both sides to the x power, right? So you could do x to the log base x of 243 equals x to the minus 5. Well, x to the log x cancels, so this is just 243 equals x to the minus 5. Right? And from there, you could solve either of these two ways. All right, that's problem 2. A lot of different ways to go about it. Pick your favorite. Right, so here we're going to use limits to see if these exist. Lost our formula sheet. Use the properties of limits. And of course, if you were curious about the properties of logs and like how you can move that stuff around, right? I know these all in my head, but of course you could check on any of these, right? So here we had log base a of x to the r. We can bring powers down, right? Of course, that's what we wanted to do. Log base a of a is 1. We use that one too. Okay. Limits. So here we're going to have some stuff on limits too. Finding limits in infinity, right? There's a whole method. So finding limits in infinity, what does it say? So if f is a fraction, a ratio of polynomials, and we can find the limit to plus or minus infinity by dividing p and q by the highest power of q, where q looks like it was the denominator here. So highest power in the denominator, right, is x squared, right? So we're going to divide both the top and the bottom by x squared. So we're going to have the limit as x goes to infinity of 2x squared minus 7x to the 4th times 1 over x squared, right? This whole thing. And then 9x squared plus 5x minus 6 times 1 over x squared, right? It's going to be equal to the limit x goes to infinity, right? This through here is going to be 2 minus 7x squared, and then we're going to have 9 plus 5 over x minus 6 over x squared, right? We know that these limits of 1 over x to the power go to 0, so these are going to go to 0. So it's going to be equal to limit as x goes to infinity of 2 minus 7x squared over 9, right? And as x goes to infinity, you know, as x goes off to infinity, this x squared shoots off to positive infinity, right? But it's negative, right? So this function is going to be going to negative infinity. There's a negative power on the x squared, right? So there's negative infinity. Here, right, we want to plug in 3, right? We can't plug in 3. So we'll try to factor. Can't plug in 3 bottom because the bottom is 0, right? So we'll try to factor, right? So x squared plus 9, you know, we can try to factor this, but it turns out we can't, right? We can't factor this, right? So this is going to mean that the limit does not exist, right? If we could factor it, right? Say we did a different problem, limit x squared minus 9 over x minus 3 as x goes to 3. Right, this one would factor, right? So it's going to be the limit as x goes to 3 of x plus 3, x minus 3, just as a practice example, right? These cancel. This is limit as x goes to 3 of x plus 3, right? Which is, plug it in, 6, right? All right, that's problem 3. Problem 4, we're going to find the value of k that makes this function continuous. Well, what does it mean for continuity? Right, a function is continuous if it's defined. It's continuous at a point, c, any point c. If it's defined there, if the limit exists, and the limit equals the value at that point, right? So what we're going to need to do is, we know that x squared plus k, it's a polynomial. So it's continuous everywhere, right? And so is this, right? But because we've matched these two functions together, right, we might have that they're not continuous where we stuck them together. So that's the x equals 2 where it switches off, right? So this would be at our x equals 2. So we don't know if these are continuous there, right? We want to find a value k that makes them continuous. So, all right, f of 2. So we can check each of these. 1, f of 2 defined, right? That's going to be f of 2, right? X is less than or equal to 2 is going to be x squared. It's going to be 2 squared, right? We're plugging it in plus k. Right, so it's 4 plus k. So we're good. 4 plus k is always going to be defined for any k. Point 2, we're going to want to check that the limit exists, right? And for the limit to exist, limit as x goes to 2, we're going to, of f of x exist, right? For it to exist, we're going to need that the limit as x approaches 2 from the minus side of f of x is equal to the limit as x approaches 2 from the positive side of f of x. When x is negative, or left of 2, right, this is going to be, this function f of x is the x squared plus k, as x goes to 2 from the negative, right? And as x goes to 2 from the positive, right, f of x is k x minus 10, right? So we're in this function. So these are polynomials, so we can plug in for x. So this is 4 plus k equals 2x minus 10, right? So we can solve this, right? We're going to have minus k equals minus 14, or k equals 14, right? And so that value of k satisfies definition 3, right? And of course, if we have k equals 14, right, you can check part 3, it'll work, right? Because the limit at 2 is going to be the value of 2, because we just made it that. So really, it comes down to setting the two functions equal where x is plugged into as 2. Right? All right, problem 5. Okay. So this is some of the research that people in my group do, trying to figure out who are the bots on Twitter. Right? Okay. So we're measuring the word decay rate. So we're going to model this as n to the minus gamma, where gamma is the decay rate, n is the number of words, and we've picked a particular gamma here. So we want to find the average word decay rate. So this is the average rate of change. Average rate of change. Right, so we're going to see this is f of b minus f of a over b minus a. Doesn't really matter which you picked from a to b, you'll get the same answer. Right, so here we're going to pick, we'll pick this is b and this is a. So we're going to have r of 30 minus r of 2 over 30 minus 2, right? R of 30, so this is going to be 5 times 30 to the minus 0.2 minus 5 times 2 to the minus 0.2, right, over 28, right? And you can go ahead and plug this into your calculator, right? And you'll get the right answer here. Maybe I'll go ahead and do it. To the minus 0.2 power. I think I can do that on my iPhone. I don't have a graphic calculator. So let's see here. Okay, calculator. Here we go. So let's try this. So we're going to want 30 to the minus 0.2, right? We can do second power, 10 to the x, e to the x. I'm not sure we can do it on here. X to the y. Here we go. To the 0.2. There we go, 1.9. This is 5 times, well, here's multiplied by 5. So this is 9.871. Right, minus, let's try this one. So 2 x to the y, 0.2 times 5, right? This is going to be 5.74 over 28, right? So let's subtract that, 9.871, right? So this whole thing is going to be 4.12 over 28, right? And so if we divide this by 28, right, this is going to be 0.147. It's negative because I subtracted them backwards. Okay. So that is the average word decay rate between n equals 2 and n equals 30. Right, we're going to find the instantaneous rate of change. Right, you could use the limit definition for the instantaneous rate of change, right? But we know, from here, but we know that the instantaneous rate of change is also the same as the derivative, right? So this is the derivative. So we can take the derivative to do this problem for us. If you tried to use this limit, it would be, you'd get stuck because you have 0.2 powers and it's kind of messy. So r prime of n, right? We're going to take the derivative. This is going to be 5 times minus 0.2, right? Bring that power down, n to the minus 1.2, right? So this is going to be minus n to the minus 1.2. And so we're going to plug in 2. R prime of 2 equals minus 2 to the minus 1.2, right? And so we can do that. We need our scientific calculator here. Clear. So we're going to have 2 x to the y minus 1.2 power, right? So this is going to be 0.8. This is going to be equal to minus 0.8. All right, and we're done. Okay. Problem 6, for the given function, find the equation of the secant line through the points where x have the given values, and the equation of the tangent line where x has a second value. So we're going to find the secant through there. So we're going to use point slope form. So we're going to have y minus y1 equals m times x minus x1 for our secant line, right? And we're going to need to find the slope for the secant line, right? So the slope m is going to be delta y over delta x, right? Which is for us going to be f of 9 minus f of 4 all over 9 minus 4, right? If we plug in 9 to this, we can plug this right in. So we're going to have 3 times 3, which is 9 to the 1/2, plus 9 to the 3/2 power is going to be 27, right, over, it's going to be minus. Plug in 2, we're going to get, or we plug in 4, we're going to get 3 times 2 plus, if we do this, we're going to get 8, right, over 9 minus 4. So this is going to be equal to 9 plus 27 minus 6 minus 8 over 5, right? And the slope is, what do we get? That's plus 1, right? Minus 5. So this is 22/5. 22/5, right? And so we're going to have, for the secant line, we're going to have y minus our first y1 point, f of 9, right here is 35, equals m, our slope, 22 over 5 times x minus the x point. We chose the 9 point for that, so x minus 9. Right, our slope of the tangent line. We're going to need f prime, so f prime of x, right, is going to be 3/2 x to the minus 1/2 for the first one, plus 3/2 x to the 1/2 for the second one. Okay, and if we plug in f prime of 4, right, we're going to have 3/2 times 1/2 plus 3/2 times 2. Those are going to cancel, so we're going to have 3/4 plus 3, right? So we're going to have 3/4 plus 3, so 12/4, 15/4, right? Because this is 3/4, and that's 3, so that is 12/4. So we're going to have 15/4. So we're going to have y minus the y of the y value at 4, because that's the point we want to do. Oh, we want to do second value. We want to plug in the other one. So f prime of 9. So this is going to be 3/2 times 1/3 plus 3/2 times 3. Right, this one's messier. So this is equal to 9/2, and this is 3/6, 1/2 plus 9/2, right? 9/2. 3/6 is 1/2. So this is actually 5. Oh, that's better. So let's do, so then we're going to have y minus, for the second point, the y value is 35, equals 5 times x minus 9. So I guess you can see that the tangent line has a steeper slope than the secant line. All right, problem 6. Moving on, problem 7. So we're going to find the derivative of this function, right? This was kind of a trick, right? You could do it using the chain rule, right? So y prime, right, is going to be, or dy dx, right? And dy dx, y prime, or y prime of x, however you want to write it, right, is going to be equal to, we'll do the log, derivative of the log is going to be 1 over the thing on the inside times the derivative of the thing on the inside. Derivative of e to the x squared is e to the x squared times derivative of the inside, which is 2x. Right? Well, 1 over e to the x squared times e to the x squared cancels. It's just 1. So this is just 2x. We're done. Right? You could have also said, oh, well, if I rewrite y is equal to ln of e to the x squared. Well, ln of e to something, right? We could bring this down. This is x squared times ln of e. Right? And of course, ln of e, log base e of e is just 1. So y is just equal to x squared. So if you saw that, it was an easier problem. But either way, you're going to get 2x. Right? Derivative of this is, of course, 2x. Find derivatives of the functions defined as follows. Okay, so here we go. We're going to take derivative of this. So it looks like we're going to need the quotient rule. So f prime of t, right? Quotient rule, we're going to have the derivative of the top, right? Which is going to be 9e to the 2x times the chain rule of 2 times the bottom, 4x plus 3, minus the top, 9e to the 2x times the bottom, derivative of the bottom, which is 4 over 4x plus 3 squared. Sorry, bud. Finn is barking at the UPS guy. All right. And we're done with that one, right? We could simplify this, right? So this is what? 9e to the 2x. Then you have 2 times 4x plus 3 minus 4. Yeah. That's okay. Why does this factor out? Can we do this? So this is 9e to the 2x. This is 8x plus 6 minus 4. So it's 8x plus 2 over 4x plus 3 squared. Okay, fine. Problem 9. All right, so a rectangular tank with a square base, an open top, and a volume of 4765 feet cubed is to be constructed of sheet steel. Find the dimensions of minimum surface area. Okay. Of course, we can do that. So, first thing to do is going to be give ourselves a useful sketch here. So here's our rectangular tank, right? Right, it has sides and a base, right? No top, right? So we have the volume, which is going to equal. We know it has a square base, so x, and y. Y is the height, x is the side of the base, right? The volume is going to be x squared y, base width times height times length, right? Which is going to equal 4765. Right, the surface area, which is what we want to minimize, is going to be the base, right, plus the 4 sides. There's 4 sides which have size x, y. Right, we have 2 variables in here, so I'm going to plug in for the y, right? You could also plug in for the x. I'm plugging in for the y by rewriting v, right? So this is going to tell us if I divide both sides by x squared, that y equals 4765 over x squared. Right, so if I plug in here, we're going to have x squared plus 4 times x. Plug in for y, we're going to have 4765 over x squared. Right, so this is equal to x squared plus 4 times 4765 over x. You have one x underneath left, and so we'll take the derivative. S prime of x, right, is going to be 2x, right, and then minus 4 times 4765 over x squared. This is x to the minus 1. Drop the minus 1 down, you get minus 2, or squared on the bottom. And so we're going to want to set this equal to 0 to find critical points. So we're going to have 0 equal to 2x minus 4 times 4765 over x squared. So we'll move this over. So we're going to have 4 times 4765 over x squared equals 2x. Multiply both sides by x squared. 4 times 4765 equals 2x cubed. So 2 times 4765 equals x cubed. Divide both sides by 2. Right, and so x is going to equal the cube root of 2 times 4765. Right, and this is going to be in feet. We're taking the cube root of this, which is feet cubed. So we're going to have just feet left. And so if we do this, we're going to have 2 times 4765, right? And we're going to take the square root. Oh no, that's not what we want to do. Undo. 2 times 4765, right? And we're going to cube root. This is equal to 21.2 feet, right? And we could plug back in. So if we do, we take x, we square it, right? And we divide 4765 by that, right? Right, so we have this, and we want to divide 4765. So we can divide it by 4765, right, and then invert it. So this is y, and so this is for x, and then y equals 10.6 feet. Of course, it's half of that, right? So we found a box that has 20 feet wide by 10 feet tall. Right? Okay. And problem 10, use implicit differentiation to find dy dt. All right, so we're going to go ahead and differentiate. Sometimes it's helpful to write y as a function of x because it is a function of x, but we don't need to here. So the derivative of the log, right, is 1 over whatever was inside times the derivative of what was inside. So I'm going to use the product rule. So first times derivative of the second plus the second times derivative of the first. It's just 1, right? And then that was that term. So then we're going to have, oh, right, and then times dy dx, right? And then we're going to have this term, which is going to be, drop the power down, so it's going to be y times dy dx, and derivative of e to the x squared, right, is 2x e to the x squared, right, chain rule. It's still going to be equal to 0. So terms that we have with dy dx's, so we're going to have x times 3y squared over xy cubed, which is this first term here, times dy dx, right? And then we're going to have plus the second term, right, which is y cubed over xy cubed, that term, plus y dy dx, plus 2x e to the x squared, equals 0. So I'm going to subtract this term and this term over. So we have the x times 3y squared over x times y cubed times dy dx equals, so we're going to have plus y dy dx, right, equals minus 2x e to the x squared minus y cubed over xy cubed. Probably cancel those. Okay, so if we go ahead and pull out dy dx, right, we're going to have dy dx times x 3y squared over xy cubed plus y equals this thing, right? So dy dx is going to equal this thing, minus 2x e to the x squared minus y cubed over xy cubed over this, which is x 3y squared over xy cubed plus y. Right? If I do simplify these, right, those x's cancel, y squared cancels, so this is equal, so we have 3 over y plus y on the bottom, on the top, minus 2x e to the x squared, and then this should cancel, it should just be minus 1 over x. That's a little bit better, right? So that's that one, and we're done. Good job.